All right, welcome everyone to the third lecture of our PWF Quantum Machine Learning course. I'm glad to see a lot of faces coming back here and hopefully enjoying the course. We just had a great talk by Juan Miguel about quantum chemistry. So hopefully some of the things that we saw last class were useful to enhance your understanding and appreciation of Juan Miguel's great talk. So today, let me briefly explain what's the goal for today's class. We're going to keep studying some of the different implementations for variational quantum algorithms. We already saw quantum chemistry, quantum algorithm, how we can try to encode the problem into a cost function that we can evaluate into a quantum computer. What are the different aspects of the cost function that we would like to have? And how do we build circuits to try to train a quantum state that is going to be the solution to that quantum chemistry problem, right? So now we're going to see other implementations. Specifically, we're going to analyze how we can use quantum computers to study problems that maybe are not quantum in themselves, but rather are classical. So we have a classical problem. It has nothing quantum in it, but we still want to use a quantum computer to try to solve that problem. So today, we're going to be studying a little bit of that. We're also going to be studying ansatz design. So we have this parametrized quantum circuit, U of theta. We've just said that a couple of times. We might have some information as to how to build it, like we did with the unitary coupled clustered ansatz for quantum chemistry. But we will also see what type of parametrized quantum circuits we can use whenever we have no information about the problem. And we will also see if all the different cost functions and all the different type of ansatzes are born equal. Maybe there's some difference between them, and maybe there's some that we want to use. Maybe there's some that we want to avoid. So we're going to see if we can reach that by the end of today's lecture. And if not, we will leave that for tomorrow. So just like we've been doing, let me briefly recap what we did in yesterday's class. So yesterday's class, we started analyzing the state of a single qubit. We said that the postulates of quantum mechanics are the things that are going to allow us to understand how to do quantum computing. Then we studied the state of a single qubit. We saw that a single qubit is a two-dimensional, is represented by a two-dimensional complex vector in a two-dimensional complex vector space, which we usually plot through the block sphere. We analyze how to extract information out of that qubit by performing measurements in the 0 and 1 basis. And we specifically look at how to compute, for instance, the expectation value of the Z operator as a function of those measurement outcomes. Because again, everything that we can do in a quantum computer is just measure, usually in the computational basis, that it's in the basis of Z, and just get bit strings at the end of the circuit, right? We measure, we get zeros or ones, and that's pretty much what we have to work with. Then we saw how to get expectation values of operators that are perhaps not in the Z basis, like how we can compute the expectation value of X. I'm going to come back to this in just a second. And then we started seeing, all right, so we have the basic framework for quantum computing. How do we use that for quantum mechanics? How do we actually use that for quantum computing? And we were basing ourselves in the DiVincenzo criteria for quantum computing. That tells us that we need to have well-characterized qubits. We need to be able to initialize them in some quantum state. We need to have a universal set of gates, which are gates that allow us to implement any unitary. And we have to be able to measure qubits. We need to be able to have qubits that are high quality. That means that they have long decoherence times. And that while noise is going to affect them, we can probably finish our algorithm before the decoherence takes over. So then we went to the specifics of near-term quantum computing, which is variational quantum algorithms and quantum machine learning. So here we saw that there's many applications for variational quantum algorithms. They all share the same structure where we encode the problem into a cost function, we define an ansatz for the circuit, and we use a quantum computer to compute and estimate that cost function, and a classical computer to train the parameters in that parametrized quantum circuit to try to get a desired output. So for instance, in the variational quantum eigensolver quantum chemistry implementation that we saw, the output is going to be a quantum state that is the ground state of the Hamiltonian that we're searching for, right? Then we're asking ourselves, how do we actually build a cost function for quantum machine learning and variational quantum algorithms? So the first thing that we need to do is guarantee that the cost function fulfills a sequence of conditions, like we want it to be faithful, operationally meaningful. It needs to be efficiently estimated on a quantum computer. Maybe it's not efficiently estimated on a classical computer. We want it to be trainable and noise resilient. And we gave the example of preparing the ground state of the Z operator. So here we saw that this is usually a problem that is encoded into the ground state of finding the ground state of a Hermitian operator. And doing this means that we have a lot of those guarantees like faithfulness and operationally meaningful. That is going to hold true for all the cost functions that are encoded into finding the ground state of some Hermitian operator. Then we define an ansatz for that unitary, which is just how the gates are arranged, like what gates are we placing and where are we placing them. And we want to have a circuit to extract information and measure and estimate the cost function, right? And we saw all throughout this the problem of finding the ground state of the Z operator. Our first example was the variational quantum eigensolver, which is perhaps the most famous quantum algorithm. Juan Miguel talked quite a lot about that algorithm in his talk today. And he also talked quite a lot about quantum chemistry, which is sort of what we reviewed during last talk. He mentioned the Jordan-Wigner, the Braff-Kitaev transformation, and all this mapping that we have to do to be able to take a problem that is intrinsically a molecular Hamiltonian problem and map it into a Hamiltonian that we can measure into a quantum computer. Then we saw that the quantum circuit that we're going to build for this case is called the unitary coupled clustered ansatz, and it leads to circuits that sort of look like this whenever we have to exponentiate those operators that we're going to be calling polystrings. So for today's class, the first thing that I want to do before going to the next variational algorithm is just briefly go back and review some of the tips that we've been doing that we've been giving for quantum computing, because some of those tips I think are extremely important and are going to play a very big role in the future. So first, whenever we had our cost function, we said that our cost function was going to be of the form C of theta, where again here I'm going to try to maintain the theta vector whenever it's appropriate. But I might fail at this, and please don't hold me accountable. I guess that via context, you're going to know which one I mean. We have our initial state, rho 0, that we're evolving through a parametrized quantum circuit, and we're measuring the expectation value of some Hermitian operator O at the end. This translates into a picture that roughly looks like this. Have an initial state, rho 0. I send it through a parametrized quantum circuit, and at the end, I perform measurements. Right? So this is sort of like the general framework that we're going to be working with. And of course, the question that we want to try to ask here is, all right, so how do we extract information from the measurements to compute this expectation value, right? So the first thing that we said is that O is usually going to be of two forms. It's of two forms. The first is whenever we assume that O is expanded in terms of polystrings, which we've already talked about, but I want to properly define them. So this is why I wanted to go back to this. So we assume that O can be efficiently expanded into a summation of those sigma i's, where here sigma I is essentially going to be X, Y, Z identity, tensor, N. So we've already used this notation in the past. What is this set right here? We're going to call this here the set of polystrings. So let's see what this means, this notation right here. So this notation right here means that if we have n qubits, we're going to have n spaces where we're going to build a tensor product operator. And the first, for instance, in the first qubit, we might have a Z operator. So we have a Z on the first qubit, a Z on the second qubit, and then the rest are just identities, right? Because we can take any element from this set and just tensor product on all the qubits. So this could look, for instance, like this. We can also write this as Z1, Z2, right? But we can also have longer polystrings, like the ones that we've already seen here. Like this one right here is a polystring on 4 qubits, which was of the form, why not? I'm going to be starting with 1 today. I'm not going to use computational notation. Tensor Z2, tensor Z3, tensor Z4. For 1 qubit, we already talked about just Z and just X. But for multiple qubits, we have this whole family and this whole set of operators that we can build where at each qubit, we either put an X, Y, Z, or identity, right? And those are essentially the basis in which we're going to be working with. And we want the summation to to have the summation, for this to be efficiently computable, we usually assume that the summation has a polynomial number of terms. Polynomial number of terms, right? The second type of cost function that we're going to be trying to estimate on a quantum computer are the ones where the observable operator is going to be expressed as a summation over I. Let's use now the letter D. And here we have Z. Now we are trying to measure the projector onto some state Z. And moreover, we are going to assume that the state Z belongs now to the computational basis of n qubits. So again, we're going to be using this notation right here. So what does this mean right here? For instance, we already know that this right here, oh, this is belongs, this is not equal. This right here means that these are all the elements in the computational basis for n qubits. So why do we assume that are always going to be on either of those two forms? And of course, here we also assume that the summation has a polynomial number of terms so that we can efficiently estimate it on a quantum computer. So the question is, how do we take those operators and estimate them via measurements on the quantum computer, right? Because all that we can do here at the end is, we said, we measure in the computational basis, and that's all that we have. So let's start with case B. How do we go about how to estimate the cost through measurements that are usually projective measurements in the computational basis? Right? Because that's the whole point. We need to have a cost function that we're going to be able to estimate in my quantum computer. And we said that one of the criteria for the cost function is that it can be efficiently estimated. So let's start with B. So B, what do we have? Let's take the cost function and let's just replace O by this equation right here. So we're going to have something that looks like, see, I'm already forgetting the vector. And we're going to have a summation of I, di, z, z. We can, of course, take the summation out. Again, via linearity of the trace, u of theta, u dagger of theta, z, z. And we already know that the trace with a projector is just the expectation value over that projector. So we know that here we can write this as u of theta, rho 0, u dagger of theta, z, right? And moreover, because we remember the postulates of quantum mechanics, we exactly know what this is, because this is exactly performing a measurement in the computational basis. And this should be, for completeness, zi. So let me add it everywhere, because otherwise the summation makes no sense. So this should have an I here. Right, it's just some bit string. So this is going to be the summation over I of di, the number of times, the probability of measuring the qubits and obtaining the bit string zi, right? So for instance, imagine that my cost function, let me give you a more specific example. The summation of I of di, zi is going to be the summation, it's just going to be projector onto the old zero state, right? So we only have one term in the summation. So we just, it's just one specific case. And in this case, the cost function is simply going to be the probability of measuring the old 0-bit string, right? And this is something that we can probably efficiently estimate. All that we have to do is we have to measure all of our qubits a bunch of times, and we see how many times we got that bit string outcome. So this can be estimated in a quantum computer by, we don't have to do anything. We just run our circuit and literally use this one right here, measuring the computational basis. This is one way to do it. There's other ways, as we will see later. P, paste, we're going to put this here. And we can estimate this as the summation of Di, the number of times we got Zi outcome over the total of measurement outcomes, right? And that's it. That's what we have to do. Of course, there could be other complications than one can get here. Imagine that you have many qubits. Imagine that you have 50 qubits. And then how many outcomes do you have? 2 to the 50. That is a bunch of outcomes. And maybe the old zero state is not the most probable one. As we see, this can actually give us some problem. But imagine that I don't want to do this. I don't want to just have to measure a bunch of times and try to randomly see how many of those times we get the zero outcome. So the question is, well, this is an efficient circuit and an efficient way that we can estimate the cost. It's not efficient. It is a way in which we can estimate cost functions with operators as in B. There are other ways that we can do this. And here I'm going to introduce tip. I don't even remember what this tip is. Let's just scroll quickly up here and check. Tip number 6. And again, remember, I told you last class that you should think about quantum computing as Legos. What you're going to have is you're going to have a collection of tools and small bits and pieces that we're going to combine to be able to do more interesting stuff. So here, let me introduce an extremely useful circuit, which is called, I'm going to introduce 2 circuits here. So I'm going to take a nice mathematical sidestep to introduce 2 circuits, and we're going to see how those circuits can be used, for instance, to also estimate this cost function, because that's the whole point. There is not a single way to estimate a cost function. There could be multiple ways in which you could estimate it. So I'm going to introduce a circuit which we like a lot, which is called the Hadamard Tests. This is part of the exercises in our theory exercises. So I'm going to maybe not go into all the details that go into proving the results for the Hadamard test, because part of the goal of this course is for you to prove them. So what is the Hadamard test? So let's say that we have a state psi, right? And we wanted to, and this state psi can be psi is general in qubit state, right? And we have a unitary U. And U is a unitary operator. The Hadamard tests allows me to compute things like the real part of psi U psi and the imaginary part of psi U psi. Of course, why do I have to compute the real part and the imaginary part? Because U is not necessarily Hermitian. So its eigenvalues, or whenever we take the inner product with a vector, it doesn't necessarily have to be real valued, right? It's going to be a complex number in general. That's why we have the real and the imaginary part. So how does the Hadamard test work? So what we need to do is first we need 1 extra qubit, which we usually call an ancilla. Ancilla means auxiliary qubit, which means that we're going to be using to aid in our computation, right? And we're going to have our n qubit state psi. So, you know, this is a circuit that sort of looks like this. And what the Hadamard test is, first, it, as the name suggests, it applies a Hadamard gate to my ancilla qubit, where here the Hadamard gate, we've already talked about this, is a gate that looks like this, and that it maps the 0 state to the plus state, 0 plus 1, which is equal plus the eigenvalue of x associated with the plus, the eigenvector of plus associated with the plus eigenvalue, and it maps the minus to 1 over square root of 2, 0 minus 1, which is the minus state, right? So then what we're going to do is we're going to control this unitary right here, which is the unitary that we want to compute the expectation value of, right? Then we're going to take this qubit. We're going to make another Hadamard gate. And finally, we're going to measure just the ancilla qubits. We're not going to measure all the n qubits. So what does this big thing that we have right here mean, this controlled unitary? So we've already talked about the control not gate, right? Which means that when the control qubit is on 0, this gate does nothing. When the control qubit is in 1, it does whatever it's controlling. So a controlled unitary, you can always think about a controlled U, which is this gate right here. And we can think it about if the ancilla qubit, so I'm going to use this as an A with ancilla so that we can keep track of it, is on 0, the gate does nothing on the second system, right? This is an identity on n qubits, which is the identity on this system right here. I'm going to call this ancilla system, and I'm going to label this identity on the system so that we know who's acting on what, to be completely clear. But if the ancilla qubit is in 1, then I apply the unitary to the system, right? So again, control operations are very simple. If the control is in 0, it does something. If the control, it does nothing. If the control is in 1, it does something. So let me briefly explain what is going on here. We can I'm actually going to go back on what I said, and I'm going to give you some tips on how to solve this exercise, because I think that it's good to understand how do we do circuit analysis, right? Because whenever we have a circuit and we know what the circuit does, so we know that this circuit somehow is going to help us evaluate these quantities, how do we prove that the circuit actually does this, right? So the way in which we analyze circuits is that we know what the initial state is, and we can try to keep track of how that state changes as it evolves through the circuit, right? So for instance, we can try to say, we know, okay, so let's call this initial moment, right? So, and this is T0. And we know that at T0, our state is in 0 in A tensor psi my system, right? That's all. Then let's call this right here T1, so just the first Hadamard has acted on the ancilla, and we already know how the Hadamard acts. So we know that this puts us in a superposition of the form 0 in the ancilla plus 1 in the ancilla. And we have this tensor psi. Of course, we can expand this 1 over square root of 2. And this is going to be 0 on A tensor psi, because we know that the tensor product is distributive with respect to the summation on A tensor psi, right? So then we have to apply the controlled unitary. So let's call this T2. So this was T1. T2, we have the controlled unitary. What is the effect of the controlled unitary? Well, let's take our state and take a look. We know that if our ancilla is in 0, we do nothing. If our ancilla is in 1, we apply the unitary, right? This is literally what we just said that the control unitary does. Then we know that we also have to apply this other Hadamard. So let's call this T3, and that's the state that we're going to be measuring. So here we have another Hadamard, and the Hadamard is acting on the ancilla qubit, right? So first, the Hadamard is going to act on the 0. We know what happens again. We get 1 over square root of 2, 0 on A plus 1 on A, and this is tensor psi. And we know the second term, whenever our ancilla was in 1, we know what it does because it's right here. So it maps us to 0 on A minus 1 on A, tensor U psi, right? We can just take this equation, try to reorder it a little bit. First, we're going to get a factor 1/2 at the beginning, and then let's try to pull the 0, the states of the ancilla as a common factor, right? So we have 0 on A, which is together in tensor product with, we have this right here, psi, and then we have this right here, plus U psi. And then we have the terms that are multiplying the qubit, the ancilla qubit in 1. We have, again, psi, but now this gives us a minus sign, so we have minus U psi. Right? And this is the result that we get. And this is a quantum state that we know gets to the end of the circuit. And what we want to do with this quantum state is measure the ancilla qubit in 0. So this measurement operator, we know that whenever we're just measuring 1 qubit, we can model this as a measurement of 0 on the ancilla qubit. And it's going to be, I project my ancilla qubit onto 0, and I do nothing in the identity, right? Let's call this psi final, which is the final state. And what we need to do is compute the expectation value of this measurement operator that only measures the qubit A over the state psi f, psi f. This is going to be the probability of measuring the ancilla qubit on 0. What we can do, and I'm going to leave this final part as the homework, we can prove that the probability of the ancilla qubit being on 0 equals to 1/2 1 plus the real part of psi u psi. So interestingly enough, this circuit right here allows us to compute the expectation value of some operator, of some unitary operator u over a quantum state psi. And this is extremely, extremely powerful because it gives us a way, by measuring just 1 qubit, managing to compute the real part. We can also try to see how the circuit gets modified to compute the imaginary part. But for now, let's just stick on this. The real part of some unitary operator, right? But you might be saying, this is still not what we want. What we wanted to do was compute something that looks like this. And this is nowhere near what we have down there, right? Because how do we do this? How do we go about trying to use the Hadamard test to compute this cost function? Well, now I'm going to introduce a second circuit that is extremely useful. That is called, first, the swap circuit, and the swap operator. So let's underline them. That's already underlined. So given 2 qubits, 2 single qubit systems, psi and phi, there is a very useful quantum operator that is just written as this. And this, what it does is that it gives me phi and psi. So we usually write this swap with this notation right here. And the action, as that circuit on the left tells us, is that it takes a product state and it just swaps the state over the systems, right? There is more about this in the theoretical exercises guideline. For now, let's just assume that this is something that we have. And you can generalize swap for not just 1 qubit states, but for multiple qubit states, right? So let's just take this as a granted. So the interesting thing here is that now we can try to combine the previous Hadamard test with the swap circuit to compute things that are going to look exactly like this. And this is going to be very useful, not just for this algorithm, but for many algorithms that we're going to see now in just a second. So we can introduce, for instance, what is called the Hadamard swap tests. So now you can see why I was telling you that quantum circuits and quantum computing can be thought of about Legos that you're piecing together to do more interesting things, right? So how does the Hadamard swap test does? First, it has an ancilla. Then I have system A that I'm going to initialize in psi, right? This is going to be an n-qubit system. So I'm going to use the similar notation of I have multiple lines. And then I have system B phi that is also an n-qubit system, right? And I'm going to combine the 2 previous circuits. So first I'm going to do this. This looks very similar. But here what I'm going to do is that I'm going to control the swap operator, right? So this swap, we already know what it does. It swaps me psi and phi. I'm going to take this here, H, and I'm going to measure the qubit. And I want to try to get what's the probability of the ancilla being in 0. So we can try to work out the math. Something extremely similar to this is going to happen. In fact, we can use most of this result right here to try to see how the final state is going to look at the end of the circuit. I'm not going to go through all the math because the whole point of this lecture is not for you to see me do linear algebra, but more importantly for you to try to see how you can generalize one circuit into the next, right? So what are the things that we need to change? So previously, the input state in the system was psi. That is no longer true. Because what do we start here? It was psi phi, right? Because you can think about the circuit as I just put all of this into one big block that I call psi, and I just call this u, right? So what does this tells us? That from the previous notation, psi should not have used this psi here. Let me call everything tilde, so that we can differentiate the new psi from the previous psi. So the psi that we saw in the previous circuit here is going to be the new psi tilde times phi tilde. So this is translating results. And u is equal swap, right, from the previous notation. So everything where we had this here, we just have to take and replace, here we said that we had psi gets replaced by psi tilde tensor phi tilde. Here we have u psi, but because it's a swap, we have something that looks like this, right? And similarly here with a minus sign. So we're going to have something that looks like psi tilde, phi tilde, phi tilde, psi tilde. And the same result that we previously had is going to hold, because the circuit is completely general, right? So what's the probability of measuring on the zero state is given to this. Now we have to use our dictionary to how to transform one result from the other. So we said psi, and I'm going to write here what we're translating. So we had psi, u, psi. So we said that psi gets replaced by psi tilde, phi tilde. U gets replaced by a swap, and here psi gets replaced by psi tilde, phi tilde, right? And we know the action of the swap on this. So we know that this is 1/2 1 plus the real part of psi tilde, phi tilde, and here we just apply the swap, psi, right? Now this is starting to shape up more something that I like. And here you have to be careful that this is a tensor product, right? This is a tensor product, this is a tensor product. And we use the fact that A tensor B times C tensor D is equal to A times C. So if you multiply two operators that are tensor product, then you get the tensor product of their product. So this tells us that this is 1/2 1 plus the real part. I multiply this times this. So I have psi phi times, and here I have phi psi, because now I multiply this with this. And this is nothing more than 1/2 of 1 plus the real part of the inner product between psi and phi squared, which we know this is a real number, so we can just get rid of the real part. This is just 1/2 1 plus psi tilde phi tilde. So now you can see that the swap test, whenever combined with the Hadamard test, allows me to do something that is non-trivial. It allows me to compute the expectation value, the inner product between two vectors, which is something that, it's not obvious how we can do this, right? But now we have a circuit that actually does this. So why did we did all of this big detour, right? Because we were wondering how to compute this cost function. Imagine that I want to compute the probability of the old zero state, right? We know that our cost function, as we said, going back, our cost function, and everything is going to make sense right now, I promise. For that specific example, was C of theta was equal the probability of the old zero state which was simply take the all zero state and compute the expectation value of U. This should not be dagger. Rho 0, U dagger of theta, all 0. Right? This was the special case that we wanted to do. But we said, there could be a problem with finite statistics that maybe we have to measure. Oh, I don't know what I did here. Let me go back. There it is. We were saying maybe trying to just wait for mother log we measure a bunch of times and we expect to get the all zero outcome. Maybe that's not the best approach. Maybe there's a different way to compute this inner product. Well, there is. There actually is. And for now, we know that if rho 0, it's a pure state, like we've been assuming thus far, this is going to be nothing more and nothing less than the inner product between the all zero state and apply U theta to psi 0. So now you see why this and this are so similar, because now we have a quantum circuit that allows us to compute this probability, which is the probability which is obtained as the overlap between two quantum states, without having to rely on maybe finding the probability of one bit strings among an exponentially large number of bit strings, right? We don't have to rely on luck anymore. So this detour is for you to know that quantum computing, it's all about having all of those small pieces and then trying to see how we put them together to do something interesting and non-trivial. So what would be the circuit that we use to estimate this cost function? Because remember, that's one of the things that we need for a cost function. We need a circuit that is going to allow us to efficiently estimate this cost function. So now we said we take an ancilla, like we've been doing. We take our state psi naught, right? Then we take the all zero state, because that's the one that we're going to use here, right? And this is, again, system A, system B, and we do our Hadamard test. But of course, here, we also said that we want to send this through our parametrized quantum circuit, U of theta, right? We take all of those qubits in 0, we just leave them as is. And here we said we control the swap operator. We do another Hadamard to complete the Hadamard test, and we measure. So this is a circuit that allows us to compute that cost function that we had up there, this cost function right here. So of course, there are some things that are going to come into play. For instance, before, if we are running this circuit to estimate the cost function, this is a circuit that only requires n qubits, right? So this requires n qubits to run, but it has the problem that we are hoping to get something like one probability among many probabilities, right? So maybe we don't want that. So maybe we want to use the Hadamard swap test. Now, how many qubits does this require? This requires n qubits here, 1 qubit here, 2n plus 1 qubit. So there is always a trade-off. There is always something where we're going to take a number of qubits and we're going to increase the number of qubits that will allow us to sort of narrow down that probability and try to just get that probability that we're trying to estimate. But it's going to come at the cost of additional qubits. And also imagine that our circuit U had a depth of L. So now we start to do like a resource analysis. How many qubits do we need to estimate my cost function? What's the depth of the circuit? Imagine that this has L gates in parallel. Well, this circuit has L gates here, but I also have to implement this control swap operator. And doing a control swap operator usually requires a bunch of CNOTs. And this is a non-trivial thing that we need to do. And this is usually going to be a circuit that has a depth that is order poly n. So we also come at the cost of 2n plus 1 qubits plus additional order poly n circuit depth. So again, there is no free lunch in quantum computing. You want to do something, but you're going to have a problem. The thing is that this is still polynomial, right? So we're not incurring into an exponential depth. So we have a question from YouTube that says, if we are interested in state preparation and define the cost function as fidelity, then how to deal with that? The cost function estimation using state tomography might be exponentially costly. Right. So here my question is, you are defining your cost function as the fidelity between two quantum states, right? So the question from YouTube is telling us we have a cost function, and it's going to be defined as, for instance, the fidelity between two quantum states. So I have a target state and the variational state that I'm trying to prepare, right? And we can define this cost function. We want it to be faithful, so we want the minimum to be equal to 0. So for instance, we define it like this, because we know that if psi of theta is equal to psi target, let's use different notation here. We've been abusing psi quite a bit. Let's use chi target up to a global phase, which is unmeasurable due to this. Then C of theta is equal to 0. Why is it equal to 0? Because the overlap between a state within itself would be equal to 1, and would get something that looks like 1 minus 1. So in this case, the question is, how do we evaluate this cost function? So one way, as suggested by YouTube, is we do full state tomography, which is we try to extract all the matrix elements of psi. That's what tomography means. I learn all the elements in the decomposition of this state, say in the computational basis or in the poly basis or whatever, but that's exponentially expensive. But if your cost function is like this, you don't have to worry too much. You can actually use the circuit that we have up here. Just replace the all zero state by psi target. And this circuit will allow you to compute this fidelity cost function without having to worry about doing state tomography. So the whole point is that you can actually compute fidelity, at least between pure states. Let's not talk about mixed states for now, because that's a whole different bag of cats. But at least you can compute the fidelity between mixed states using this exact same circuit that we have right here. Because this cost function, we just need to estimate in the quantum computer the overlap between two quantum states, two different quantum states. And we exactly know how to do this. And we are going to review this cost function in just a second, whenever we look at other variational quantum algorithms and how to define circuits and cost functions to evaluate them. So thank you very much to whomever was on YouTube, and I hope that answers the question. Just you can send another comment. I'm going to have some delay, so I might go back to it in a bit. Right. So a lot of things have been said. Why did we make all of this very big detour about Hadamard Test swap circuit and Hadamard swap test? Is just to say there are ways to estimate cost functions that are of this form. I wanted to give you a guarantee that if you define a cost function that is of this form, you are going to be able to estimate it on a quantum computer using different tricks. There could be other ways in which you could do this, but for now, let's just assume that we're going to stick with those two. Now, the other question that we want to try to answer is, how do we estimate the expectation value of operators in the form of A? And this is going to back to something that I promised at the end of last class, which was I'm going to teach you how to estimate expectation value of poly operators, of poly strings, because we already know how to do that for like single poly operators, but now we want to estimate expectation value of multi-qubit poly operators, which is like the type of operators that you get in quantum chemistry, for example. So those are extremely, extremely useful. So in this case, let's just go back. We said that our cost function was going to be of this form, where sigma I is just some polystring. So it belongs to the set X, Y, Z identity tensor N. So we go back to our cost function. And now let me just try to speed up ahead a little bit. And we have that this is what we need to do. We need to estimate something that looks like U of theta applied to our initial state, U dagger of theta sigma I. So in this case, again, this is the expectation value of psi naught U dagger of theta sigma I U of theta psi naught, because again, we have a projector. So we know how to compute this trace. The trace of a projector is just the expectation value of whatever operator you have in there over your projector. So this is what we need to do. So we need to compute essentially a summation of expectation values of our states sigma I over our evolved states U of psi none. So how do we go about doing this, right? So what do we know? We know that if sigma I equals Z on some qubit, right, on qubit K, then we just measure that qubit K. So for instance, in this case, we have a circuit that will look like I start in psi none, I apply U of theta, right? And then I just measure the kth qubit. My measurement outcomes are going to be 0 on the kth qubit and 1 on the kth qubit. I'm just measuring 1 qubit, so I will just get 0 or 1 on that 1 qubit. And we know that the expectation value is going to be computed by the probability. So the expectation value of Z K, and I'm just recovering some of the results that we previously know, is the probability that the kth qubit is on 0 minus the probability that the kth qubit is on 1, right? This is just reviewing some of the results that we had previously seen. If people have questions about this, we've already seen this, but I would be happy to review how we get to this result. So are there any questions up to this point while we're reviewing some of those results? All right, I guess not. So let's keep going. So let's say that now what happens if sigma I is equal, for instance, X on the kth operator. Well, we already saw that we can compute this expectation value using a very similar circuit, right? But we need to perform a change of basis in my measurement, because we can always think about this as I measure Z. What I want to do is I want to measure in the basis of X. And we know that a measurement in the basis of X is exactly the same as I measure in Z, but before the measurement, I just implement a change of basis operator. For instance, a Hadamard gate, because we already know that a Hadamard gate maps me between the basis of Z and the basis of X. So this is precisely what I'm going to be doing. I'm going to be adding here one Hadamard gate, and then I'm going to be doing my usual measurement, which is what we can physically do in my quantum computer, which is I just measure this 1 qubit on Z. So how do I know that this is true? How do I know that this is a measurement that if I get, how do I interpret the results here? Because I have the circuit, and again, I will always get 0 or 1. That's all I get, right? But how do I interpret that result of 0 and 1? Well, let's think about in this circuit right here, what does it mean to get measurement outcome? So if I have pk equals 0, what does this mean? What is this exactly? Well, we know that we have here the expectation value of, I take my states, I evolve it through U. I have here sign on, U dagger of theta. And at the end, I'm going to be implementing a Hadamard just on the kth qubit. The way that we say this is I have a Hadamard on the k qubit and nothing else on the rest of the qubits, which I'm going to denote as k bar, is just the complement of k, which is the identity on the rest of the qubits, right? So this is going to be hk dagger, which is equal to hk via the identity times the identity on the rest of the qubits. And then the probability is just I'm measuring and projecting the 0 qubit onto the 0 state. So here, what we have is the measurement operator. So this right here is going to be the measurement operator of getting the kth qubits onto 0. I'm using a lot of different notations. I'm going to start being consistent. I'm going to use the superscripts for the qubit that I'm talking about. So this is the projecting the kth qubit into 0. So this looks like this, and doing nothing else to the rest of the qubits, right? So this is the expectation value that we're doing. So essentially, this is the state that we get at the end of the circuit. This is the expectation value. This is the projector operator, the projective measurement operator, onto just the 0 qubit being on K. And what we get here is that we can use the cyclical property of the trace to take this right here. Sort of, right? And I can take this operator and cyclically permute it towards the right. So I can just do this. And put it here, right? And now let's exactly compute what this is. Let's explicitly see this. So we already know that the product of tensor product operators is the tensor product of the products, right? So this can be written as Hadamard in the kth qubit, acting on 0, 0 in the kth qubit, Hadamard in the kth qubit, tensor, identity times identity times identity, which is an identity, right? And what is Hadamard acting on 0? Well, we already know this. This is the plus state on the kth qubit. So now, if we rewrite this here, we have our state that has evolved through the circuit. And here we have this operator right here. And just if we see this, what is this right here? This is a projective measurement operator on the kth qubit onto the plus state. So what we're doing is exactly what we set out to do. We are making a projective measurement onto the plus state in the k qubit. But what's interesting here is that this still is a probability of 0, because when we measure, we don't measure plus or minus. We still only measure 0 or 1. What changes is the interpretation of what that probability means. Because we did a change of basis, now the measurement outcome is telling us the probability of projecting onto the plus state of x, right? So this is how we know that we can reinterpret the probabilities. And now we just do the same, and we just compute x as the probability using this circuit with the change of basis of the qubit k being on 0 minus the probability of the qubit k being on 1. And that's how we can do the change of basis, right? Now let's go to something more complicated. How do we go about computing expectation value, for instance, of 2 poly bodies? So imagine that now. Let's compute the expectation value of 2 body poly, that should be uppercase, that's a proper name, operators. So for instance, we want to compute the expectation value of Z1, Z2, right? How do we go ahead and do this? Well, the first thing that we need to recall is that we were able to derive the result that the expectation value of Z was expressed as the probability of 0 minus the probability of 1, based on the fact that Z is equal to projector onto 0 minus projector onto 1, right? This is what we did. So let's use a trick again. Let's say Z1 is just projector onto the first qubit being on 1, tensor projector onto the first, minus projector onto the first qubit being on 1. And Z2 is going to be 0, 0, 2 minus 1, 1, 2. So what is Z1, Z2? This is going to be this product right here. We're going to have 0, 0 minus 1, 1. Everything is in 1. Tensor product 0, 0, 2 minus 1, 1, 1, 2. And we actually know how to do this tensor product. This is just 0, 0, 0, 0, where this is qubit 1, qubit 2, qubit 1, qubit 2, minus 0, 1, 0, 1, qubit 1, qubit 2, qubit 1, qubit 2, minus 1, 0, 1, 0, qubit 1, qubit 2, qubit 1, qubit 2, plus 1, 1, 1, 1, 1, 2, 1, 2. So essentially, what this equation right here tells us is that we can also estimate the expectation value of ZZ by measuring 2 qubits. How do we do this? So the expectation value of Z1, Z2, we measure qubit 1, we measure qubit 2, and we just compute the probability of 0, 0 on qubit 1 and qubit 2, plus the probability of 1, 1 on qubit 1 and qubit 2, we have a plus here, minus the probability of 0, 1, minus the probability of 1, 0. This is qubit 1, 2, qubit 1, 2. So how does this circuit actually look like? So what we have here is our state sign on, qubit 1, qubit 2, the rest of the qubits, we evolve them through U of theta. We measure qubit 1, we measure qubit 2, and we don't do anything else to the rest of the qubits. And by just computing how many times out of those 2 measurements we got 0, 0 outcome, 0, 1 outcome, 1, 0 outcome, and 1, 1 outcome, we can estimate this cost function through the expectation value, through just the summation of frequencies of how many times we got those measurement outcomes, right? So whenever we actually perform the measurement, Z1, Z2, you know, this is just going to be the number of times that we got 0, 0, plus the number of times we got 1, 1, number of times 0, 1, number of times 1, 0, divided by the total number of shots that we did. So we can use the same trick that we did before, but now with multi-qubit operators. And of course, the logical question, the next question is, what happens whenever we want to try to compute expectation values of Z1, X2? You know, we're not going to go through a whole hassle again, but you can probably already see where this is going. We're going to use the same circuit, copy, paste. What do we need to do? We need to make a change of basis here. We're going to add here a Hadamard, and we're going to here measure. And the expectation value of Z1, X1 is going to have this form. But now again, we know that whenever we measure the second qubit, and it's on 0 and in 1, the second qubit, we're actually measuring in the basis of Z. So the interpretation is still correct. The formula will look exactly like the same. We measure both qubits. We do number of times 0, 0, plus number of times was 1, 1, minus number of times 0, 1, minus number of times 1, 0, divided by the total number of measurements. But now the interpretation is different because we did a change of basis. And that's going to be extremely, extremely important to note that even if the formula looks the same, we know that we did a change of basis. And that's how we can estimate this, right? So, you know, just for completeness, I wanted to make that comment before pasting this formula. Oh, not copy. But we know that once again, we are going to compute this in this way, right? So now we know how to do this, and we can generalize this to multi-qubit strings. You just measure the qubits that are in the polystrings and change an appropriate change of basis, and you're going to be doing a summation that is weighted with plus or minus signs out of those probabilities that you get at the end that are given by a product that arises sort of this form, right? Of course, there's many questions that arise here. One of them could be, for instance, how efficient this is, right? How many times do I have to use my quantum circuit to estimate all of those terms in a cost function that is of this form? Well, in principle, you could say, right, so imagine that I have here poly n times, and let's copy this. So now let's do what we did here, which is an efficiency analysis, right? Here we said, you know, we were looking for just one bit string. That bit string might be exponentially small. We might need to measure a bunch of times. It's not obvious how many measurements we need to do, but we can have this Hadamard swap test circuit, which at the cost of additional depth and qubits, we can sort of restrict the space where we're looking for probabilities to just measuring one qubit and have a better chance of estimating the probability that we're trying to get, right? So let's try to do here resource analysis, right? So let me just put this here, resource analysis. And I'm just gonna write here again, resource analysis, because that's what we were doing here. And this type of research analysis is extremely important whenever you're trying to decide, given your quantum algorithm, what circuit am I going to use to estimate my cost function, right? So this is extremely crucial to the design of cost functions and circuits for estimating your variational algorithm. So we said that O is going to be a summation of I of Ci di. Sorry, this is sigma I. So we knew that estimating sigma I requires a circuit with maybe some change of bases, some change of bases. So imagine that I have here in the summation poly and terms, as we've assumed. And each time that we run a circuit, maybe we have one body terms, and we're going to measure just one qubit. Then we have two body terms, and we're going to be measuring 2 qubits, right? So how many times do we have to run our circuit? So if each time that we're doing this, we have n measurement shots, the total budget for this could be in principle poly n times n measurement shots. So here we have estimating requires a circuit with maybe some change of basis and local measurements. This is what we've seen. But of course, you can see that a lot of times we're running quantum circuits where we're not measuring all the qubits. So here we wanted to estimate Z1 and Z2, and we only measured 2 qubits, Z1 and Z2. The rest of the qubits, we just trace them out. We're not doing anything to them. It almost seems like a waste of resources to prepare an n qubit state and then just measure 2 of them. And the rest of the qubits are just, we're doing nothing to them. So the question is, can we still measure those other qubits? Can we try to use the fact that we've already prepared our initial state? We've already sent it through a parametrized quantum circuit. Can we measure maybe more qubits at the end and still try to recover, for instance, the expectation value of Z1, Z2? So here, let's do a little example, which is I have a 4-qubit state. And I want to estimate Z1, Z2, and Z3, Z4. From our previous example, what we said that we had to do was 1, 2, 3, 4. Prepare a sign node, evolve it through U of theta. First, we measure these 2. The other 2, we don't do anything, and this allows us to estimate Z1, Z2. And then we do something similar. We restart everything. We run our quantum algorithm again. Big N times, this is n shots. This is n shots. And here we wanted to estimate Z3, Z4, where we measure here, and we measure here, right? So this is 2 n shots. Is this the best that we can do? Can we actually estimate both Z1, Z2, Z3, and those 2 expectation values in one go? Let me just pause for a second and let me try to ask the class if you can you think of a way in how we can actually estimate all of those expectation values at once? Does anyone have any idea? Or maybe you can just say, no, I don't think you can compute all of those expectation values at once. Right, so Jorge Avalos says that we can maybe do 4 measurements instead of just 2. So how would we go about doing this, right? And that is correct. There is a way in which we can estimate all of those 4 by measuring all 4 qubits. So now we can think about a circuit where we are going to measure all the qubits. Let me try to redraw this in a cleaner fashion. 1, 2, 3, 4 smaller boxes so that everyone fits. Sorry, I have this notifications that are popping up. Let me quickly try to get rid of them. Oh, that's the tab. Yeah, sorry about that. All right. And how do we do this? So what are the outcomes that we get out of here? So again, everything that we get in quantum computer are just bit strings. So everything that we can get here is the probability of 0, 0, 0, 0, probability of 1, 0, 0, 0, probability of 0, 1, 0, 0, and all the way down to the probability of 1, 1, 1, 1. How many probabilities do I have? I have 2 to the 4, which is 16 outcomes, right? This is all that I'm going to get. I measure all the qubits, all that I can get, and it's given number of times I got all 0 state, given number of times I got this bit string, and so forth, right? So, but those probabilities are not the ones that we have in these formulas right here, right? The estimating Z1 and Z2 requires me the probability of just 0, 0. I don't need the probability of everyone being on 0. But of course, the beautiful thing is that we can use marginal probabilities. And marginal probabilities tells us that there is a way to compute the probability of 0, 0 via this probabilities right here. So what is marginal probabilities? Marginal probabilities tells me that if I have 2 random variables, xi and x and y, let me do it like this. I have the probability of 2 variables. I can always get the probability of x, for instance, I, taking value I, by just taking the probability of xi and adding over all the outcomes possible for j, right? And this is extremely powerful because let's think about this. This tells us that the probability on 0 on 1, 0 on 2 is going to be equal to the probability of all bit strings that have 0 on 1 and 0 on 2, and I need to add over everything else. So I have to do this. All the bit strings have to start with 0, 0. Remember that, because that's what we're doing using this formula. 0, 0, 1, 0, plus probability of 0, 0, 1, 1. So we can actually compute the probability of just the 2 qubits, the first 2 qubits being on 0, by making this summation right here and doing the marginal probability, right? And then we can see that by measuring 4 qubits, we can recover this formula. We just have to re-express this as marginal probabilities, like we're doing right here. So this allows us to compute both Z1, Z2, Z3, Z4 with n measurements. Why is this true? Why can we actually do this, right? Is it true that we can always compute the expectation value of any number of polystrings by just measuring n times? Well, no, because again, it's not as easy, right? What do these two operators have in common? So let's think about what they actually are. Z1, I'm going to be extremely explicit. Z1, Z2, in our notation means identity on 3, identity on 4. And here, Z3, Z4 means identity in 1, tensor identity in 2, tensor Z3, tensor Z4. And something that those two operators have in common, and this is going to be the key aspect, is that they commute. Z1, Z2, Z3, Z4 commute. And if you remember from your quantum mechanics course, we know that operators that commute can be simultaneously diagonalized. If they can be simultaneously diagonalized, that means that there is a basis that is going to be a basis of eigenvectors for all of them. Moreover, what do we do when we measure? We are going to be measured on the basis of some operators. So all that we need to do to estimate those expectation values is measuring their common basis. What is the common basis of Z1, Z2, Z3, Z4? It's the computational basis. So we get this for free. But again, this is not true. We will not be able to do this for any set of operators. For instance, if I have X2, Z3, well, let's do actually X2, X3. Well, the problem is that X2, X3 does not commute with Z1, Z2, because X2, X, and Z on the qubit 2 do not commute. So this is different than 0. And it's going to be the same problem with Z3, Z4. We cannot, on the same run, try to estimate the expectation value of these two, because we're going to have a problem. They do not commute. So we cannot estimate their expectation values by measuring on the same bases. But for instance, if we take X3, X4, can we come up with a circuit that is going to allow us to simultaneously estimate Z1, Z2, X3, X4? Well, yes, because these two commute. If it's not obvious to you why these two commute, think about this as an identity in 3 and an identity in 4. And the identity in 3 commutes with X, the identity in 4 commutes with X. So if we wanted to estimate both C1, Z2, and X3, X4, we just do the circuit, but we insert a change of basis measurement of change of basis right here. So those two are operators that we can simultaneously diagonalize and hence simultaneously get their expectation values. So again, this is where linear algebra and your knowledge about properties of, for instance, matrix that can be simultaneously diagonalized, we can actually get their expectation values with the same number of shots. This is where you start using your knowledge about quantum mechanics and about algebra to improve your quantum circuits. And there is a lot of work being done on this. For instance, let's go back to quantum chemistry for just a second. In quantum chemistry, we said that we started with a molecular Hamiltonian that is written in the position and momentum terminology. We second quantized it. We did Jordan-Wigner mapping, and we got something that looks exactly like what we're doing. We're going to be having operators that are just the tensor product of polys. It's just a summation of polystrings. So this is an exact Hamiltonian of the form of what we've been looking at. And a lot of people have been working in ways of clustering the terms in this Hamiltonian in commuting terms so that you can try to estimate this expectation value using the least amount of resources possible. So this is extremely important and extremely useful, right? And but now let's go back to this, because again, there is never a free lunch, right? There's never a free lunch. So what is the problem about doing this this marginal probabilities? We are, at the end of the day, imagine that you have n qubits, right? If we have n qubits and we just wanted to estimate a bunch of 2 local terms, sorry about that, we have a bunch of measurement outcomes, and each one of them has an uncertainty of 1 over square root of n. So if I say, okay, I want to estimate Z1, Z2 as a summation of probabilities, of weighted probabilities, C, let's call this, use a different letter, Q, let's use I, probability 0, let's use different letters, sorry. I want to try to be clear, so let's just here use mu, and you're going to see what this means in a second. I, J, right? So this is just some weight via the probability of measuring Ij, where this is either +1 or -1. So this formula right here is precisely of this form. It's just probability of 0, 0 with a 1, probability of 1, 1 with a 1, probability of 0, 1 with a minus, probability of 1, 0 with a minus. But we've already said that, in turn, this can be expressed as a summation of Qij mu via some other weighting that we're going to get right here of probabilities of bit strings, right? Now, this is full n length bit strings. This is n length bit strings, right? That will have the qubit I such that Ci equals to I and Zj equals to j. Because what are we using here? We are just replacing via this equation right here. So this is a summation of a bunch of terms. And whenever we know that we're estimating probabilities, each probability is going to have a statistical uncertainty given by the measurement shots, by the number of measurements that we're doing. So we can try to do an error analysis. And I know that I'm jumping between a lot of things right here, but I just want you to know that all of this, even if it's not clear right now, is just to say that there is no one way or one simple thing that we can do. There's a lot of small technical issues that are going to start popping here and there. It's like you have a dam and it's leaking water, and you put your hand to try to block the water in one part, but that makes it break in another part. And you try to block that, but that makes another part get water. So you're trying to fight against all the different sources of uncertainty or error that you can have, right? So what is the error analysis for estimated a quantity such as this right here, which is a summation? So if we do the error propagation formula, we know that, the uncertainty of a function of x1, xn is just going to be the summation over I of the absolute value of the partial derivatives of xi with respect to their uncertainties, right? So this is going to be expressed using this formula. The uncertainty of computing this expectation value through measuring all the qubits as a summation qij mu, right? We're going to get an absolute value here. This is a +1 or a -1, so this is just going to go away, of the expectation value of each probability. So the only problem that we have here is that the errors that we have in each individual probabilities are going to stack up. And if we have a large number of qubits, that's going to be stacking up a lot of errors, because we have to do a very specific summation of probabilities, and those probabilities have small errors. There's ways in which we can improve. This is an upper bound, because we're just doing this in a very brute force way. But this is just to say that this actually adds a lot of error, and you have to be careful about this, because we're, again, estimating a big number of probabilities, and each one of those probabilities is going to have some error. And whenever we do some linear combinations with them, that is also going to have some error, right? So that error is going to get propagated. That 1 over square root of n, that finite measurement shot, which clearly defines quantum mechanics and clearly defines quantum computing through the fact that quantum computing is probabilistic, is going to be all over the place. And you always have to keep your mind on this. So finally, before wrapping up this first part of the class, which took a little bit longer, but I think that this is very useful to try to broaden your mind and the way that you think about quantum computing and all of those small issues that arise, I also wanted to say that there's another way in which you can compute the expectation value of polystrings. And again, let's just go back to some of the useful circuits that we have. Let's see the circuit right here, the Hadamard test. The Hadamard test, we know that it can compute the expectation value of some unitary, right? It allows us to compute something that looks like this. So let's just go to the bottom and think about making a note here. Note. We can also compute the expectation value of a polystring. For instance, and this is specifically useful whenever you have like very big polystrings and you have to measure a lot of qubits, right? Sigma I via the Hadamard tests. How? We start with an ancilla qubit, as we always do. We start with our system, C0. We have our Hadamard. Here, we are going to send this through my U of theta. What is the unitary that I have to control now? Well, it's very simple. I just have to control the unitary, that is sigma I. And it's pretty obvious that sigma I, for any sigma I that is a polystring, you can always double check that this is a unitary. That sigma I times sigma I dagger. First of all, it's Hermitian. So this is just equal to sigma I is equal to the identity. And we can think about Z1, Z2 times Z1, Z2 is just equal to Z1 times Z1 tensor Z2 times Z2. And of course, you know that this is identity, tensor identity, right? So we just do this, do our Hadamard test, we measure, and we know that the probability of the ancilla qubit being non-zero is going to be 1/2 of 1 plus, again, this unitary is Hermitian, so no real part, expectation value of sigma I. So this is another way that you can use another circuit to compute the expectation value of sigma I. And the nice thing about the circuit is that it's actually not a difficult circuit to implement, because controlling polys is precisely one of the simplest things to do, right? For instance, controlling poly in X, that's just by definition a CNOT. So this is a circuit that is very useful, and we can also use to estimate expectation value of polys. So this has been a lot, I know. We're going to try to tone back the linear algebra in just a second, but I thought that it was useful to give you a little bit more tools, because, again, let me just rephrase this, and I'm going to sound like a broken record. Quantum computing is about understanding that you have a set of rules and a set of constraints that you have to keep in mind. Those constraints are, for instance, I can only measure in the computational basis. I have to build my cost function from that. How do I do that? Well, maybe I need to compute the probability of a given bit string, because that's how my cost function is defined, right? Maybe I need to compute the expectation value of some poly operator. Well, how do I do that? There's different ways. But what's interesting is that with the circuits that we have right now, it's more than enough to understand the vast majority of quantum circuits that are going to be out there. In one way or another, they're just doing cost functions of the form of A and B. So now you have these tools under your belt to understand whenever it tells you, oh, I need to estimate this cost function. You can just look at the cost function and be able to answer the question, can I efficiently estimate this? If it doesn't fall within this category, you might have to do something else. Maybe you have to combine those circuits that we've presented with something weirder or something more interesting. But for now, you already have this set of tools that you know how you can use them as moving parts in building your quantum algorithm, right? So I think that this is a good stopping point for a break. When we start, I'm just gonna give you a little spoiler so that you're gonna get your coffee and be like, oh, I want to get back to the class. We are going to look at another extremely famous variational algorithm. So we have a question. A polystring of n poly operators would be exponentially costly. Aha, that is a great question. So the question, and before I go to what's the next step, is assume sigma I acts non-trivially. So that's the way that we can phrase it. This non-trivially means that there is no identities, right? For instance, Z1, Z2 acts trivially on all but 2 qubits. So now we want a polystring that has x's, y, z's on all the qubits. That acts non-trivially on all n qubits. So, is there a quantum circuit to estimate this? Sure. All that we have to do, take our state, send it through U of theta, and just do an appropriate change of basis. So in the first qubit, it's z, I just measure, right? Second qubit, it's x, then I change of basis with the Hadamard. Third qubit is a y, then I do a change of basis with a rotation around the y-axis. And fourth qubit, and so forth, I will do my changes of bases as appropriate, and then I will measure. And then I know that whenever I do this trick of writing the expectation value as a summation of probabilities, I'm going to have an exponential number of terms, because I have all the possible outcomes. They are weighted with pluses and minuses, but I have an exponential number of terms. So something that you can always do is try to estimate this with a finite number of shots. Of course, this will come at the cost of you are going to have some statistical error, and those statistical errors are going to start piling up very fast. The other thing that you can do is just essentially do the Hadamard test, because the Hadamard test is going to come at the cost whenever I have to control this poly. So if we use the Hadamard test, it's going to come at the cost of controlling sigma i's. But what is sigma I if we think about it? And let's be more explicit about this. Sigma I is just, we said in this example right here, 4 qubits, this was Z on the first qubit. That's why we didn't change of basis. X on the second qubit, Y on the 3 qubits, Z on the 4th qubit, right? This is just following our previous 4 qubit example. And I need to control this, right? How would I go about doing this? Well, this is just the same as I have my ancilla qubit. So I have my ancilla that first controls Z. Then I have my ancilla that controls X. Then I have my ancilla that controls Y. Then I have my ancilla that controls Z. Why is this so easy? Because this is a tensor product. Polystrings, and estimating the expectation value of polystrings, this is just a tensor product. And controlling a tensor product is the same as controlling each individual one of them. You can actually see that this is true by just writing each one of those individually and making the matrix multiplication, in the sense that the first one is I do 0. If my first qubit is in 0, I do Z1. And if my first qubit is in 1, sorry, this is identity, right? I do Z1. And then I implement the second one, right? What does the second one do? So the second one is telling me if my first qubit is in 0, I do nothing. If my ancilla qubit is in 1, I do X2, right? Whenever I multiply those two matrices, it's straightforward to verify that you get this. 1. And here I have tensor X2 Z1. So you can see that just concatenating them like this, you're going to build it. So there is a way to avoid that exponential cost at the cost of controlling those polys. And this is going to add, again, this is resource analysis, so I'm going to use this color. So you're going to get plus order and depth in the circuit. So the depth of controlling a K-body, K-body poly, a K-body poly string with poly as in the proper name, adds a depth order n. So in this case, you could try to avoid that exponential scaling by doing the swap test, and it's going to add some depth and then ancilla, right? So there's always a cost. There's always something that you're going to have to pay. So I hope that answers the question. So before our break, again, let me just quickly say what we're going to be seeing now. The next thing that we're going to be seeing is the QAOA algorithm, extremely famous algorithm. It's called the quantum approximation optimization algorithm. And it's a quantum algorithm to solve classical problems. Those problems have nothing quantum in them. It's that we're just going to put them in a quantum computer and try to solve them. So we're going to be back, everyone. I will see you here in, let's give everyone 17 minutes. So let's get back here at 12:50 for you all. And I'm going to make me a coffee and see everyone in just a bit. So Felipe, if you're ready to pause the YouTube stream, I'll see everyone in just a couple of minutes. All right, welcome back everyone to the second part of today's lecture. So during this second part, what I'm going to try to do is I might go faster on some things. I don't want to linger too much in the details because the idea is not for this to be a specific course on just quantum circuits that you can use for quantum computing, but rather to give you a big overview. I think that the previous discussion was good and necessary. We went into a little bit more detail that we've had for other things, which I think is going to be useful to understand some of the results that are going to come afterwards. But we still have quite a bit of ground to cover. So let's start going. So QAOA, this is one of the most famous quantum algorithms out there. It was developed by Farhi and al. You can find this paper in the archive as 14114028. So what is this quantum approximation optimization algorithm? So this is an algorithm that used for solving combinatorial problems in quantum computing, in quantum computers. So what are combinatorial problems? Well, combinatorial problems are usually used for, and they appear in problems such as logistics, supply chains, developing networks, even things like sending taxis to customers and fixing their rates. Optimal delivery rate routes for whenever you're sending out packages. And for more important and crucial aspects of life, such as water and electricity supply lines. So these are problems that, as you can see, they have nothing to do with quantum. They have nothing to do with quantum systems. They have nothing to do with quantum computing. They're purely classical problems. And moreover, they're problems that have a lot of real-world implications with a lot of economical impact to them. And usually what these problems have is that, in general, they are very hard to solve because you just have a lot of aspects to the problem and a lot of moving parts that are going to come into play, and they're usually naturally in an optimization problem. Say that you have airplanes arriving at an airport and you're trying to decide which airplane is going to go at which gate so that you can optimize passenger travel so that the passengers are in average closer to the destination so that they don't miss their flights. So a lot of those problems are very hard and they just have a lot of variables to them, and you cannot just explore all the different combinations until to find the best. So formally speaking, what we have is, and let's try to give this a formulation, a mathematical formulation. So let's try to formalize. Formally speaking, a combinatorial, and let's start going back to this red color for important thing. Combinatorial optimization problem is defined as a task of determining there it is, an optimal object out of a finite set of objects. So here, more specifically, and just to simplify our life, we will focus on the problem where we want to find an optimal bit string. That is, we want to find an optimal sequence of zeros and ones. more specifically, and so that we can narrow it down just a little bit further to go to a specific case, we will consider combinatorial optimization problems on graphs. And specifically, we will consider the max cut problem. So what is the max cut problem? Let's try to define it first. I'm going to define it with words, and then I'm going to draw a couple of pictures that might hopefully help you understand the problem better. So this is a problem of partitioning the nodes on the graph into two sets, such that the number of edges between the sets is maximum. That's a mouthful. What are we talking about here? So let's give a specific example. Imagine that we have a graph. Graphs are defined in terms of nodes and edges. So let me copy this 4 times because we're going to use it 4 times. Copy. So this is the graph that we're going to be considering. It has 4 nodes and 4 edges, right? And the goal is that we want to try to draw a line that separates those nodes into 2 sets. So we can draw one line and say, you know, all the points that are on the top half of that line are going to belong to one of the sets. All the nodes that belong to the bottom part of that line are going to belong to the other set. So we can draw, for instance, a line here, and we say all the nodes that are on top are going to be blue. All the nodes that are below are going to be green. Let's actually use this. This is going to be easier. So we said blue and green. This is green, 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 green. This is, of course, not the only solution. We could do something different, such as like this. So this, we're again partitioning our graph into 2 sets. One is giving us 3 nodes in one set, and 1 node. Oh, this is too similar. Let's use yellow. I think that the line is yellow. Red. Yes, that's much better, right? We can also have other examples, such as doing this, which is going to give me now 2 states in each set, right? 2 red and 2 green. Or we can even do something even fancier, right? We can do something that sort of looks like this. So in this case, we are going to have these 2 are green. These 2 are blue, right? Moreover, what we can do is that we can now start asking the question that the problem asks. We want to partition the graph into 2 sets. We've already done this by drawing a line through the graph that gives me some nodes that are going to be in the top part. You know, top is relative. I'm just defining this as an example, and all the nodes on the bottom part as belonging to 2 different sets. And we want that the number of edges between the set is maximum. So what does this mean? So here we only have 1 set, and the line is crossing no edges. So this would be assigned, according to this problem, a value of 0, because there are 0 edges between sets. We can actually do it more generally so that I don't have to copy this. Just put this. This is going to be the number of edges between sets. And that's the number right here. How many edges are here between sets? In the second one, there's 2, because we are crossing here and we're crossing here. So there's 2 edges that separate the sets. This one right here also has 2. Now, this final one actually has 4. So you can see that those different ways of partitioning the nodes in the graph have different values according to that specific task that I'm trying to solve, which is the max cut problem. And just so you know, this might seem like a very dumb problem, but there's quite a significant number of optimization problems, of real-world problems that can be mapped to something like this, just like the ones that we were previously discussing. So there's some mapping. I'm by no means an expert in that. But let's just now stick with this mathematical simple formulation, right? And of course, now we can think about, how do we know, how can we actually assign those values, right? How can we try to determine a graph, because we said that we're going to be working with bit strings? Well, something that we can do is we can always say, all right, let me just arbitrarily say this is going to be qubit number 1, or bit the bit string, the bit number 1, bit number 2, bit number 3, bit number 4. And I'm going to do the assignment, which is completely arbitrary, that this means, oh, I used the same color. That's unfortunate. There it is. I'm going to say that red means 1. This means 0. So with this arbitrary set of rules that we have set, what is the state of the first graph? Well, the bit number 1 is green, so it's 0. Bit number 2 is 0. Bit number 3 is 0. Bit number 4 is 0. This one right here would be assigned to 1, 0, 0, 0. This one right here would be 1, 1, 0, 0. Oh, I just realized that the last one, this should be red. There it is. Now it's consistent. I think at some point I just messed up the colors. Right, I like it more now. And this final one is going to be 1, 0, 1, 0. So you can see that there is an arbitrary set of rules which we have employed to map bit strings into a given value of interest that we have. So here for 4 nodes, as we said, we have 4 nodes, and each one of those nodes has 2 possible values, 0 or 1. So there's 2 to the 16 assignments. And we have to find, again, the one that gives me the maximum number of edges between the sets. So the solution here happens to be actually this one. And this solution is not uniquely defined. We can also have a solution that looks like this, where all that we have to do with this line is just flip it around in itself, such that the bottom left and the top right are now going to be red, and the other 2 are going to be green. And we're still going to get a max cut value of 4. So you can see that this problem is already starting to get interesting, right? And what this has is that, as we can expect, as the number of nodes increases, so let's just use number of nodes increases, the number of possible assignments increases exponentially. So trying to find the bit string that solves my problem with a bunch of nodes is going to become exponentially hard, right? So this is a problem where you can already start to see why maybe a quantum computer might be useful, because we're trying to explore, find some elements in an exponentially large space, right? So there's something that maybe we can do. So now let's try to go back to, it's been a while, but I'm going to scroll up because I think we're going to need it, to what are the steps that we said that we need to build what are the steps that we need to build a quantum algorithm. First, we need to define and map my problem of interest into a cost function. And second, define an answer. So let's keep those 2 into mind, because that's exactly what we're going to do with the max cut problem. So the first thing that we need is 1. We need to define a cost function. So in general, max cut problems are defined, as we said, in terms of a given graph. Because it's not just defined by the number of nodes, it's also defined by which node is connected to which other node. And a graph can always be expressed, a graph G can always be expressed as a collection of V, E, where V is a collection of nodes and E is the collection of edges. So the element here in the nodes is just going to tell me node 1, node 2, node 3, all the way to node n. And E is going to tell me node 1 is connected with node 3. Node 2 is connected with node 17, and so on and so forth. So what we need to know now is that there is usually a way to try to quantify this problem classically, right? Evaluating what's the max code value is something that we can do classically. So the object function, and I'm calling it object function and not cost function to just note that this is classical, is again, for the classical problem, let's be very explicit. Is defined on bit strings of length n, right? And essentially, all that we need to do is that this classical object function, it takes a bit string z, where we're going to be using this notation again. Now you know it. And all that it does, it makes a summation. Alpha goes from 1 to the number of edges to see if a clause is satisfied. So here, S alpha of z is equal 1 if z satisfies a given clause. So here, the clause is that the two different nodes that are connected by that edge belong to different sets, right? If z satisfies a clause and as z of z equals to 0, otherwise. And we can do this by just looking at the graph, right? If someone gives us like a coloring, a bit string, it's very easy for us to check the value of this function. Now, the question is, how do we promote this into a cost function that we can evaluate into a quantum computer? So let's promote this. We want to promote the classical object function to a quantum cost function. So here we're going to define an operator, which is going to I'm going to be calling it H sub P, P because it's defined by the problem. And we're going to make a summation over JK. This just means start thinking about qubits. And here this notation indicates edges on the graph of a local term H JK. Now let me move this around just a little bit so that we have a little bit more space, where H JK is equal to 1/2 1 minus sigma z on the qubit j, or we're using another notation. We're using like z on the qubit j, z on the qubit k. So now you start to see that this is starting to shape up like one of the cost functions that we say that we could efficiently evaluate, one which is made of a summation of Pauli operators. So how is this working, right? Imagine that you have a given bit string. So I have a given bit string z, and in this bit string k, the kth qubit is in 0, and the jth qubit is in 0. So both of them are going to be in 0. And let's assume that the edge jk belongs to the graph. So that means that there is a line whenever we drew the graph that connects the node j with the node k. So what is the value of this thing right here? So what we're going to have is here the expectation value. Whenever we compute the expectation value of this Hamiltonian, of this term right here over our quantum state, we're going to get here the expectation value of z over 0, which is going to be 1, the expectation value of z over 0, which is going to be 1, and here the expectation value z, h, j, k, z is going to be 0. And this is true if both of them are in 0, 0, or in 1, 1. But if one of the qubits is in 0, so now kth qubit in 0, and jth qubit in 1, or vice versa, 1, 0, what's going to happen is that the expectation value of this local term, I'm going to have here the expectation value of z over 0, which is 1. Here, the expectation value of z over 1, which is minus 1, right? So now these two terms are going to add up, and this is going to be adding me 1, right? So whenever I have elements that belong to different sets, now this is different than 0. And you can see how this local term is checking if the clause is satisfied or if the clause is not satisfied, right? Which is precisely what we want. Let me just check. Am I saying this correctly? If both of the qubits are in the same, we get 1, 1. And then this is 1 minus 1. Yes, this is correct. Right? So now let us go and let us define my cost function. And my cost function is simply going to be given. And if you want to minimize this, you just have to add like a minus sign up here so that this is actually minus 1 instead of maximizing, but it doesn't really matter. All that we need to do is to check that this actually gives different results if the clause is satisfied or if the clause is not satisfied. I might be missing a minus sign somewhere. I'm not really sure where. Okay. But most importantly, what we want to do is we already have a cost function that is defined by this equation right here. So we have this, and we know that the solution to the problem is the one where the most clauses are satisfied. So we can define a cost function as the QAOA cost function. As C of theta is going to be the trace of, I'm going to send a quantum state through a parametrized quantum circuit. Who would have guessed? And I'm going to compute the expectation value of this problem Hamiltonian, such that I know that the ground state, the one that satisfies the most clauses, is going to be the one that has the largest or lowest, depending if you define with plus or minus sign, energy, right? And we know that all the cost functions that are defined as trying to find the ground state of some Hamiltonian have the property of being faithful, operationally meaningful, and whatnot. So the next question that we need to ask is, we already have a quantum cost function. What is going to be the ansatz for U of theta? So I've already told you, a lot of times the circuit that we're going to be using for U or theta is very specific to the problem. That's the case for the unitary coupled clustered ansatz. You would only use that ansatz if you're doing quantum chemistry. I cannot take that ansatz and put it here because I don't expect it to work well. So maybe we need to come up with different quantum circuit that we're going to be using for this problem. And the main idea of this, of the QAOA ansatz, is that it's loosely based on the Adiabatic Theorem. And let's put this here. So what's the Adiabatic Theorem? The Adiabatic Theorem is, it tells me that if I have two problems, I'm going to call this HM, we're going to see why in a second, and HP. And HM is a simple Hamiltonian that I can prepare its ground state. So I can prepare ground state of M easily. But I'm not interested in the ground state of M. I'm interested in the ground state of P. So the Adiabatic Theorem tells me that if I take this state and I make it slowly evolve with a unitary evolution that is generated with a Hamiltonian that sort of looks like this, that interpolates between my initial Hamiltonian and the Hamiltonian that I'm trying to get to, where now S of 0 equals to 0, so that initially I'm sitting in this Hamiltonian, but at S of, let's say, final time, this is equal to 1, so that I'm sitting here. If I make this evolution slowly enough, then I can guarantee that this state is slowly going to transform into the ground state of the Hamiltonian that I'm interested in. And of course, here the slowly depends on what those Hamiltonians are, how easy it is for the ground state to actually jump to the first excited state. So it depends a lot of times of the gap between your ground state and the first excited state. But let's just not worry too much about that, because this Hamiltonian is just slowly based on this, right? So of course, the next thing that we need to do is how do we actually implement this evolution, right? So we said that we want to evolve our ground state via some evolution that is defined like this. Now, of course, my problem and this Hamiltonian, this driving, or I'm going to call it mixer, and you're going to see why in a bit, this mixing Hamiltonian, it might be hard to implement, right? It might be hard to actually implement this in practice, because maybe it's not easy to make this linear combination. And if I have a quantum circuit, I have to implement the exponentiation of some very complex Hamiltonian, and maybe I don't even know how to do that, right? So what we usually do is, the first thing that we do is that we discretize time into delta t intervals, into p delta t intervals, into p delta t intervals. So that what we say is that the evolution between my final time and my initial time is going to be by something that looks like this: Tf minus delta theta, u of delta t, comma 0. We can express this, of course, as a product when j goes from 1 to p of u g delta t, j minus 1 delta t. This is, of course, e of minus I, h evaluated at j delta t, delta t. Of course, this still doesn't solve the problem, because I still cannot implement this right here, even if it's like for a small enough interval of time that I can maybe consider this linear combination constant. So usually what I have to do here is use the formula that if I have something that looks like this, and I know that my time is small, because this is what I'm doing, I'm splitting my evolution into a bunch of small times. This is approximately going to be equal to I a x e of I b x plus order x squared. And this is, if we go back to the first class when we were discussing about big O notation, someone mentioned whenever you do a Fourier transform, you're going to get, or a series decomposition, you're going to get this big O. Yeah, this is true. This is exactly what we got here. And here, x is just the time. And if we have very small times, then we know that this is going to be approximately equal, right? So what we end up getting is that UTF0 is going to be a product of j going from 1 to p of e of minus I, 1 minus s of j delta t, h, here I have my hm, e of minus I s of j delta t, h problem delta t, right? So essentially what we're going to be doing is we're going to be applying the Hamiltonian that we're, an exponentiation generated by the Hamiltonian that we're going to be interested in, followed by a Hamiltonian that we can easily prepare the ground state of. And we're going to be interpolating between these two. So for max cut, usually the Hamiltonian that we're going to be using, like our mixer Hamiltonian, which is the way that people call it. Sometimes it's called mixer, and sometimes it's called driver Hamiltonian, which is the one that is going to be driving the evolution to the ground state of the problem Hamiltonian, is going to be hm, simply given by a summation of x on all of the qubits. So I just apply x on each one of the qubits. And this is a very nice mixer, because we know that the ground state of m is just going to be a tensor product of all the qubits in plus. So we can easily prepare this ground state, right? So how is the evolution going to look like for the QAOA circuit? So, usually we don't prepare the plus state, we prepare the old 0 state. And our initial state has to be this, because we said that what we want to do is interpolate between one ground state and the other. So we first need to prepare the plus state in all the qubits. How do we do this? We know that we have to implement Hadamards, so that we know that the state here is the plus tensor n. And then we're going to be doing this sequence of unitaries that are going to be of the form e of minus I. And I'm going to here change this thing that I get right here by this function s with the delta t. I'm just going to forget about this. I'm running a quantum circuit, a parametrized quantum circuit. I'm just going to put a parameter in there. I'm going to call it gamma 1 and HP. So first we apply HP, then we apply HM. And I'm going to call the parameter for HM u minus I beta 1 HM. Now I'm just following convention. So I stopped using theta for gamma and beta, and this is just because this is what people do. And then I'm going to repeat this. Gamma 2 HP u minus I beta 2 HM, and I'm going to repeat this. This is what we call one layer, and we have to do this P times. So here I'm going to eventually get E of minus I gamma P H problem, E of minus I beta P H mixer. And I'm going to get some parametrized state at the end. So this is usually what the QAOA ansatz looks like. It has this periodic structure of me implementing the exponentiation of two Hamiltonians of interest. And we can express this in a very close form, where now I'm going to define the gamma vector and the beta vector. And this is just essentially going to be this, let's be explicit at least one time. Mixer Hamiltonian with beta P parameter, U of problem Hamiltonian with gamma P parameter. Here we had mixer Hamiltonian with beta 1, U of problem Hamiltonian with gamma 1. Question, and this might be obvious for some of you, not for others. In this circuit, we read it from left to right. So we first apply HP. Whenever I write it here, HP with gamma 1. Whenever I write it here, HP with gamma 1 is all the way to the right. It's not in the left. Is it obvious to people why, sort of like the order inverts? Does anyone care to venture a guess?
It might be because the way we are applying the operators. I mean, the first operator that we are going to apply is the one that is on the right side, and then we are going to continue applying it.
Exactly. Because whenever we apply this to our initial state, if we re-express this, the first operator that is going to be acting on psi naught is going to be the one that is farther on the right. So whenever we draw quantum circuits, we read them from left to right. But remember, at the end of the day, this is linear algebra. And linear algebra, if I have A times B times a vector X, well, first B is going to act on X, and then A is going to act on X. So here the order gets reversed. So this is just, if it wasn't obvious to someone why we were writing it this way, right? So now we have a quantum circuit that will, an ansatz for the quantum circuit that will implement the evolution. The third thing that we need is, as we said, we need to be able to efficiently compute the cost function. So how do we compute? Sure. It's finding, yes, it's finding the optimal parameters for QAOA the same as finding the optimal path for AQC? No, it is not the same. Because in adiabatic quantum computing, you're actually trying to follow that schedule determined by your functions S. Here, you absolutely break that, right? Your parameters alpha and beta, they have nothing to do with that schedule that you have for adiabatic quantum computing. Because there is a model of quantum computing that is called adiabatic quantum computing that actually implements that. This is why we said this is loosely based. This is not exactly the Adiabatic theorem. It's just loosely based on that idea, and then we just break it and do something completely different. In adiabatic quantum computing, you actually try to do this. And this is actually, for instance, what the D-wave quantum computer does. The D-wave quantum computer actually initializes in the problem of a simple Hamiltonian, which happens to actually be this one, the mixer that we prepared, that we presented, and it slowly evolves through some schedule to the ground state of a problem of interest. This is not what we're doing here. So the parameters that you would find for AQC are not the same as QAOA, because you're breaking all of the schedule restrictions that you get with like D-wave and whatnot. I hope that answers the question. So how do we actually compute the cost function? So we know that computing this is going to be, and I'm going to save us some time, computing the expectation value JK of those H JKs. As usual, we take the summation outside of the expectation value, and we need to do this, right? So essentially, we just go here and we replace this by the explicit form of HJK, which we said that this was 1/2, 1 minus sigma, let's use the Z notation, ZJ, ZK, right? So this is essentially going to be given by 1/2 the expectation value of the operator identity, which is this one right here, and that's just 1, minus the expectation value of zj, zk. And oh, look at that. We already know how to compute the expectation value of zj, zk. And we actually know that because all the terms are z, we can just measure all the qubits in the computational basis and just compute this cost function, right? Because all the terms commute, because zj, zk commutes with zm, zp for all j, k, m, and p. So yeah, some of the tools that we've previously seen, we can use them to compute the expectation value of this cost function, right? So we already know that how some of those previous tools can be used to estimate this cost function right here. Now, of course, there's something else that you might be asking, right? So we were talking about implementing those big unitaries. Is it efficient? Like, how do we actually implement that? I want to quickly mention that because it's worth it. So I'm going to do like 2.1. We're talking about efficiency. So we know that the cost function can be efficiently estimated. How do we actually implement those operators? So first, let's do e to the minus I h mixer with some parameter beta. I believe that's beta, yes. So this is e to the minus I beta summation over I of xi. What do all the xi have in common? Xi, xj equals to 0 for all ij. And we know that e to the a plus b is going to be e to the a, e to the b exactly, with no approximation like the one that we have right here, if a and b commute, right? So because of this, what we have now is that we can just express this as a product over I going from 1 to n of e of minus I beta xi. And this is nothing but a rotation about the x-axis on some parameter beta. So how do we implement this in a quantum circuit? This is just going to be take all the qubits and do a rotation about the x-axis and apply the same angle. And this is important. Same parameter beta. So this is very simple to implement. It's just one rotation in each one of the qubits, and they all have the same angle. How do we do e of minus I gamma problem Hamiltonian? So let's be explicit. This is summation over jk of 1/2 1 minus zj zk. Okay, we know
Marco,
yeah.
there I do have a question. So, because on the Zoom we are summing over j and k, and you mentioned that cj and ck commute, we are not summing twice there.
No, because you're only adding here. That's why the summation is not over jk. So that's why I said like this notation right here. I'm just and I might have gone too fast. But this notation right here, whenever I define the cost function, it tells you that you only make a summation over the graph. So this is a summation that only adds over the graph. So you're not putting zj, zk, and zk, zj. For instance, if I have a graph where node j is connected to node k, and then I have node m, then the summation right here is going to have a term zj, zk, and a term zm, zk. It will not have a term zj, zm. So you're not adding over all the pairs. You're just adding over the pairs that are determined by your graph.
I see. Thank you for that declaration.
All right. So let's go back to this e to the minus I gamma. We can split this into a summation with an identity here, plus I gamma summation over jk bj zk. So again, because everything commutes, we can just start splitting things around. First, identity commutes with everything. So I'm going to get here a global phase, e to the minus I gamma over 2. And then I'm going to have here a product over jk. Again, zj, zk, they commute for every jk. We already know this. So I am going to be able to write here E of I gamma. I'm missing an over 2 here. Yes, there it is. Over 2 zj, zk. So what is this? This is just an exponentiation of a two-body poly, right? And how do we go about implementing this? Well, we've already sort of seen this at the end of the previous class as to how would we go about implementing operators that look like this. So we literally use that same formula. And what we get is that we can implement an operator, for instance, minus I theta z j zk. Imagine that this is the jth qubit, and this is the kth qubit. All that we have to do here in the circuit is do C naught controlled by J going into K, and here we do a rotation about Z on a parameter on an angle theta. And that's it. That's all that we need to do to implement those gates right here. So whenever we implement this, how is this going to look? And let me just for now draw this as a two-body block, right? So what we're going to have is we're going to have, of course, n qubits. Let me draw 4. 1, 2, 3, 4, right? And let's use actually the graph that we drew right here, this one, where qubit 1 was connected to 2, 2 was connected to 3, 3 was connected to 4, 4 was connected to 1. So, you know, we have to draw this 2-qubit gate, first connecting 1, 2. Then we can do this connecting 2, 3. Then we can do this connecting 3, 4. And then qubit 4 was connected with qubit 1. So we usually draw this like this to sort of indicate that this wraps around and it's connecting the last qubit with the first one. And that's that. Of course, we can be smarter. And because all the gates commute, I can actually just write this in this form. Or I'm going to take this gate and sort of put it here so that I can apply them in parallel. Because whenever I apply in parallel gates, I have less depth. This is a circuit that has depth 4. But if I do it like this, where I apply gates in parallel, now I have a circuit that has depth 2. So I can always implement all of the interactions in my graph with a sort of shallow depth circuit. I just have to be careful of putting everything together so that I can act in parallel to as many qubits as possible. And what's interesting about this is that this is a quantum circuit that has been so successful that people realize that this idea of the adiabatic evolution is not only good for solving combinatorial optimization problems, but in general for interpolating between the ground state of some easy to prepare Hamiltonian and some difficult Hamiltonian. So this is one case where, you know, people develop this problem for optimization, this ansatz for optimization tasks. But there were other people that realized that, you know, sort of this ansatz, it can be generalized and it can be used to find the ground state of any mixer Hamiltonian that you can, of course, exponentiate. That's the catch. I need to be able to exponentiate it. This one, I can easily exponentiate it because everything commutes. So, you know, if you have a very complex Hamiltonian, it's not like I can use this for like the quantum chemistry one, because I cannot exponentiate that problem Hamiltonian that has a bunch of polys that don't necessarily commute, right? But this generalization, so the generalization of the ansatz of U of theta was done in this paper by Hadfield et al., which is in Algorithms 12/2/34 2019, or you can find it in archive 1709/0348. And the thing is that here, given HM, mixer Hamiltonian, and a problem Hamiltonian, we want to find the ground state of this. And it's this exact same structure. And it's very funny because the way that people, that they called it, So a lot of times you might look at some reference and they use QAOA as the quantum alternating operator ansatz. So this is an ansatz for a quantum circuit where you alternate quantum operators. It's very simple. Unfortunately, it has the same letters as QAOA, the original quantum approximation optimization algorithm. So in the literature, you might find QAOA for an algorithm, or you might find QAOA for an ansatz. And depending on the context, you're going to know which one it is, but just be mindful that QAOA is used in the literature for two quite different things. The paper, this is a really nice paper. It's called From the Quantum Approximation Optimization Algorithm to the Quantum Alternating Operator Ansatz. I'm like, really? Come on. There's so many acronyms, so many names. You had to pick the first one, didn't you? but all right. So I think that sort of covers QAOA, which again, it's as an algorithm, not as an ansatz, which is an algorithm that we can use to try to find the ground state of Hamiltonian that encodes a classical optimization problem, like coloring the edges of a graph that has absolutely nothing quantum in it. So why do we expect there to be a quantum advantage here? Why is it that we expect the quantum algorithm to sort of find this solution faster than any classical algorithm? Well, this is sort of based on the idea that we're sort of exploring all of the Hilbert space at once, and this sort of idea of trying to use the Adiabatic theorem from mapping from one state to another state is sort of based that it's easier to convert to that probability, to that bit string faster, right? And you can even think, and this actually resonates, whenever I told you, you need to find an optimal object among a set of objects. This is very similar to Grover's algorithm, right? Grover's search algorithm, which we covered in the first class. Just I briefly told you that's a quantum algorithm for finding one element in a database. This is very similar to it. And you can actually define like a variational version of the Grover algorithm, which has this exact same form right here, which has a problem Hamiltonian and a mixer Hamiltonian that is defined, they are defined differently. They're not the ones that you have here, but that it can be used to sort of like solve this sort of problems. So, you know, you start to see how different things and ideas in the field are starting to tie together one to the other. And you're also trying to see where maybe we can get that quantum advantage from, right? From this idea that we can try to find the solution faster than the classical algorithm. Of course, Grover's algorithm is only polynomially faster than the classical algorithm. It's not exponentially faster. So the question still remains, is QAOA going to be more efficient than any classical algorithm? Well, we don't know. But we know that there is a method, sort of efficient, that we can use quantum computers to solve those classical problems, right? So we've already seen the VQE algorithm for quantum chemistry, purely quantum data, and this variational quantum algorithm for purely classical data. So before we move to the last stretch of the class, are there any questions about QAOA? Okay, I think that they're not. So what are we going to do? We already saw two quantum algorithms. What I'm going to try to do now is just extremely briefly present other ideas of quantum algorithms, because at the end of the day, this is a course about quantum machine learning, and I've been mainly talking about variational quantum algorithms. But what I want to show is that the connection between variational quantum algorithms and quantum machine learning is very diffuse. Both fields are very close one to the other, and a lot of the tools that we use in one are going to be useful in the other, right? Like actually, if you see the picture that we put up here at the beginning of last class, whenever we were showing like how are variational quantum algorithms built, this is extremely similar to how quantum machine learning models are built. You have to come up with a cost function. You have to build an ansatz. You have to estimate that cost function, and you have to optimize it, right? So variational algorithms are usually a little bit more or intuitive or physically based than quantum machine learning models. So it's always good to start understanding the tools, like the swap test, the Hadamard test, like how is the ansatz built. All of those things that we're going to be using for quantum machine learning, it's better to ground them on a physical motivated problem, and variational quantum algorithms are easier than that because we still don't have to train with quantum data. But for now, let's consider sort of like the first quantum algorithm, variational quantum algorithm, that is already a quantum machine learning model in itself. So we're going to start like diving a little bit deeper into maybe something that is closer to quantum machine learning. So let us now consider a quantum autoencoder. And again, I'm going to go super fast here. Quantum autoencoder. So autoencoder, that already sounds, for people that are familiar with machine learning, it's a very machine learning term. So what is the idea of quantum autoencoder? So the idea is that I give you a data set that is formed of quantum states, psi I, and I'm going to send you different quantum states with different probabilities. This probability is pi, right? So now we already have the notion of data, in the sense that I'm not going to be dealing with one initial trivial, simple quantum state. Now I have non-trivial quantum states. Those states, psi I, they might be something really interesting. Maybe they are like the ground states of some molecule already. Like someone prepared them and someone is handing them to me, and he's giving me, and they're giving me like a set of quantum states with given probability. And there is this paper by Romero et al. It's Quantum Science and Technology, Quantum Sci Tech, and it's 2045001 2017, or archive 1612028006. And the goal here is that we want to do lossless data compression. What does this mean? This means that I want to give you a set of quantum states, and those are n-qubit quantum states. And what I want you to do is that I want you to compress the information in this data set to a smaller number of qubits. So you can think about me having n qubits. This is information that is spread throughout n qubits, but I want to compress it, because maybe I want to send it through a quantum channel, and it's cheaper for me to send less qubits. So I want you to split this into NA and NB qubits, and I want all of this information to be encoded and compressed onto just NA qubits, and I want no information to be lost if I take the NB qubits and I just trash them, right? Why do I want to do this? Because now I'm going to get a reduced state in small number of qubits. Maybe what I can do with this is that I can take those qubits, I can send them, for instance, through some quantum channel, and then I'm going to have here, this is the encoding part. Maybe I want to do the coding, right? I want to learn how to also decode the information so that I recover my initial state on NA and NB qubits. And here, maybe I just initialize NB fresh qubits that are somewhere else, maybe in another lab, and I build my quantum my quantum state back up. So how would we go about doing this, right? How would we go about actually performing this data compression using a quantum computer? So first, for simplicity, because we're going to be sending quantum states probabilistically, we can always think about this as my initial state is mixed. So with probability pi, I send state psi I, right? So now instead of having a pure state like we've been doing thus far, we have a mixed state at the beginning. And what do we do here? So this is going to be a mixed state on NA and B qubits. So this is the D subsystem, this is the A subsystem, and we're going to send this through an encoder. What is an encoder for us? What is the way in which we process information in quantum computers? Parametrized quantum circuit, because of course it is. And then the way that we're going to do this is that we're going to require that here we can trash qubits without us losing information, right? So we want to define a cost function that compresses the state of rho into a reduced state rho A without us losing any information. So what we need to do here is we need to define a cost function. The way in which we can do this is, for instance, we can say, I want my cost function to be something of the form, I want all the qubits here to contain no information. How do I guarantee that they contain no information for any state that I send here? For instance, if I can guarantee that all the qubits in B are in 0, and they are always on 0, no matter what state I set here, then they don't have any information about rho. So if I can have a quantum circuit that maps all the qubits in B to always be in 0, I have no information about who the initial state was, right? So I can define a cost function that could be, for instance, and let me define here, a measurement operator that measures in B. So we were using this notation, right? And it's going to be identity in A tensor, all my qubits in B are in 0, right? And I want the probability of this measurement operator to be maximized, because if the probability of this measurement operator is equals to 1, that means that all the qubits in B are always on 0, and I never know any information about who the input state was. So my cost function could be, okay, I want to maximize the probability, so I can do 1 minus the probability. So I can do 1 minus the probability that all the qubits in B are on 0. How do we go about explicitly writing this? So let's go. Okay, I've been consistent here. Probability of B, all my qubits being on 0. It's very simple. I just take the trace over my unitary, apply to my initial state, evolve through the quantum circuit, and then I measure this operator. So here you can see that this operator is not exactly of the form as the ones that we had previously. It's not a summation of polystrings, and it's not the projector onto one bit string, but it is a projector onto a local bit string. So this is a local measurement. So what I'm going to be doing is, how do I evaluate that cost function? I'm going to take my quantum circuit, and I'm going to measure the qubits in B. And I'm going to check for the local probability of those qubits being on 0. And I know that if those local qubits are always on 0, then that's it. So I have an efficient way to do this. And of course, you can ask yourself, well, how do I recover information? So this is the cost evaluating circuit. Cost evaluating circuit. So how would I recover information from this? Well, it's extremely simple, right? All that I would have to do, and I can let you think about this for a while afterwards, is that I have all of those qubits that I've trashed them because I know that they are in 0, so I don't care about them. And then what I can do is put here a decoder that is U dagger of theta, where I initialize fresh qubits to 0. And if my cost function was exactly 0, that I achieved lossless compression, I know that I'm going to recover here my state rho. So this is already a nice way to see how some of the tools that we've been using thus far can start to be useful for quantum machine learning and for a purely quantum task like encoding and compressing quantum data, right? So this is already a task where we can see how we can take all of that tool frame that we've built to sort of understand this and try to understand how to actually build the quantum circuit that is going to solve the solution, that is going to find the solution to our problem. And just because this was mentioned in chat, I believe, by one of our YouTube viewers, and they were talking about fidelity. And actually, one of our students from the course yesterday was asking me, because we're using Python in our hands-on course, what is Python has this line in it that is transpiling. What does transpiling mean? So I also want to talk another variational quantum algorithm that is going to be a quantum algorithm for compilation. Algorithms. So first we need to understand what compilation and transpilation means. So compilation usually means taking a higher level code and transforming it into a lower level code that can be understood by another language. Transpiling means the same, it's only that it has the added definition that both codes need to have the same level of abstraction. Sure, whatever. In practice, for us, what compilation means is that I'm going to have a unitary U that maybe I don't know its physical description. I don't know its circuit description. And this is going back to the original thing that we said, how do we transform a unitary into a sequence of quantum gates? So I have an U that has either no efficient quantum circuit description, or maybe it's even unknown, right? Maybe this U is just given by the evolution under some unknown Hamiltonian that is hidden. Maybe it's my system evolving, and I don't know how my system evolves. And what I want to do is I want to try to take this, and this is already starting to play into quantum simulations, right? How do we simulate quantum systems? This is one way in which we could try to simulate a physical evolution that we don't have access to. We don't know how the system evolves because we don't know the Hamiltonian. But maybe what we can do is try to learn that evolution through a quantum circuit. And what Qiskit does is that usually a lot of times in Qiskit, you're going to write a quantum circuit that has a bunch of gates. Maybe those gates are not native. Maybe those are not the native gates that the physical superconducting quantum computer is going to be implementing by itself. So what you need to do is you need to transform that high-level unitary into a bunch of small gates that is going to be able to implement. To give you an example, in Qiskit, you can ask it to do a swap. But is swap a natural interaction in your superconducting quantum computer based by the physical interactions between the qubits? Most likely not. You're going to have to decompose that into a sequence of quantum gates. So what we want to get at the end here is just a given sequence of quantum gates that is going to have the same action as you. So we want to learn, and again, everything starts with the task or goal. We want to learn a quantum circuit, an efficient, let's add here, maybe short depth quantum circuit representation of a unitary. And let's just now consider the case where I only care how this unitary, and for simplicity, it's called this V, because we've been using U for our trainable unitary, right? So let's keep it U versus V. So we want to learn the representation of this, the action of this unitary V over some states. So for instance, maybe what we can do is prepare a zero state. We can send it through V. And here we're going to have V acting on 0, right? What we want to do is we want to initialize our qubit in 0. We want to send them through a quantum circuit that is parametrized. And we're going to have a state U psi of 0. And we want those two states to be exactly the same, right? This is the goal. We want U theta of 0 to match V of 0. Okay, what's the first step? First step, define a cost function. And let's put the steps here. So here I had step 1. How do we define a cost function, right? How do we go and we say we want to define a faithful cost function that is going to be 0 only to match, not math, match. So for instance, think about the cost function. C of theta is equal to 1 minus, and of course, how do we compare it to quantum states? We just compare their overlap. We see how close they are one from the other. So we do 0, then we do, for instance, the overlap between this and this. Let me dagger this one. So I'm going to have U dagger of theta. Then I'm going to do the overlap with this state, V 0. Then I'm going to have this absolute value squared. So this cost function is already very similar to something like the one that we were discussing previously whenever we were wondering how do we compute fidelities, right? The fidelity between two quantum states can be computed with the swap test. This is what we saw, right? So we already know that there's a quantum circuit to do this because this cost function is the fidelity between two quantum states. I'm taking a quantum state, I'm comparing it with another quantum state. And we know that this can be evaluated with the swap test. But in this case, it's even simpler, right? There's another way to evaluate this. Why? Because we know that this cost function copy, paste. And in principle, how do we evaluate it, right? How do we evaluate C of theta? So we already know one. We can use this Hadamard, the swap tests, which we already know. We can do the swap test. We can also do something that looks, for instance, like I initialize all my qubits in 0. And this is, again, to show that there is no one unique way to do this, right? Then I send it through my unitary V. Then I send it through my parametrized unitary U dagger of theta. And then I just measure all the qubits. If I use the circuit, this cost function right here is just the probability 1 minus the probability of all the qubits being on 0. Because why? You can think about this as I take the 0 state, I evolve it through V, I evolve it through U dagger, and I then measure all and compute the expectation value of the projector into the old 0 state, which is just the probability of 0. So this is another way in which we can define this, right? We can find the circuit to evaluate this cost function. So I think that we're nearing the end of our third class. Before wrapping up, I would like for you to notice, like, no one said anything, but we've only been talking about step 1 and step 3, which are cost definition and cost evaluation circuits. So here we had step 1, here we had step 3. We skipped step 2 for both of those. So 2. This is a question that is going to motivate the start of our next lecture. So for the autoencoder, and the compilation task, what ansatz should I use for U of theta? Can I use the QAOA ansatz? Maybe not. It's not obvious. Can I use the quantum chemistry UCC unitary coupled cluster ansatz? Absolutely not. That's definitely not going to work. So there's a lot of problems where we can take information about the problem, encode it into our ansatz, and get an ansatz that is very good for that specific problem, like we did in QAOA and UCC. But there are other cases. For instance, think about the autoencoder. Imagine that you have no information about what those states are. You know nothing about them. You don't know if they have symmetries. You don't know if they belong to the ground states of if they're ground states of a condensed matter system or maybe some molecule. I'm just literally telling you, this is a collection of states, and you just need to compress that information. And the question from YouTube is precisely the one that we're going to answer at the beginning of the next question, which is, in the autoencoder, we don't have any information that we can put into the ansatz. So what do we do then? How do we build an ansatz for problems where we don't have any information? How do we put gates? Like, you know what the gates are, the ones that you can use. We've already said that we're going to build our circuits from CNUTs and rotations. And this is what we've been doing. Those are the universal gate sets that we said that we're going to be working with. So those are just CNUTs and rotations. And the UCC ansatz was also in this form. Quickly, let me just show it. So how then do we build an ansatz just based on rotations and CNUTs for tasks where we have no problem, no information that we can embed into the problem? So this is actually going to lead us to study a very important problem and a very open and pressing question in current quantum machine learning and quantum variational algorithms, which is the ansatz design problem. So first, what we're going to do is that we're going to see that there's a type of ansatz that is called the hardware efficient ansatz, which is problem agnostic. It's in principle something that I can always use. I can always try to build an ansatz where I just put the gates in some way. We're going to see how we're going to choose the way in which you're going to put those gates and try to hope that that ansatz is good enough to find a solution. Now, of course, the problem is that that ansatz, it has no information, right? It's quite general. And we also know that nature is not friendly to computational sciences. So we probably will not be able to use a general ansatz for every problem, because there is not one hammer that is going to be useful for all the nails, right? So essentially, what we're going to see next class is we're going to see the ansatz design problem, and we're going to see how the ansatz design and the cost function and how you choose your cost function can have a significant effect on you actually being able to train those parameters. And we're going to start looking at some of the challenges of variational quantum algorithms and quantum machine learning, such as barren plateaus. That is something you might have heard of. Mira was talking a little bit about it, but we're going to see that not all ansatz are created equal. Some are not trainable. Some you just don't want to use because you're not going to be able to train the parameters. And we're actually going to analyze what does it mean untrainable, not being able to train the parameters. What does that mean? And with that starting point, next class, we're just going to look at some of the first challenges for variational quantum algorithms, because up to this point, it sounds great. It sounds like we can use variational quantum algorithms for everything, but we haven't really delved into the challenges. So we're going to take we're going to dip our fingers and our toes a little bit into the ansatz design problem, the barren plateau problem. We're also very briefly going to analyze what would be the effect of noise in variational quantum algorithms. And then we're just going to put a hard stop, and we're just going to jump to quantum machine learning. So we're going to see how some of those challenges, we're just going to put them in the back pocket for now. We're just going to say, all right, let's just hold them on for a second. Let's define the whole framework of quantum machine learning. And then at the end, and this is probably going to be on Friday, we're going to take everything together and try to see how some of the challenges that we've seen thus far are also going to be challenges of quantum machine learning. And hopefully by Friday, the answer that we're trying to answer is, where can we expect a quantum advantage for quantum machine learning? And what are the difficulties that we need to face and what that we need to be careful for in designing a quantum machine learning model that we know is going to be useful? So I hope that this was an interesting lecture for all of you. I know that you probably must be tired and hungry, so I think that this is a good stopping point for a lunch break. So I think that, Felipe, if you want to just cut the YouTube transmission for all the YouTube viewers, thank you very much for tuning in and for the awesome questions. And I'll see everyone in 1 hour, and we're going to go back to our hands-on exercises. Remember that everything was shifted by 30 minutes. That doesn't mean that you only get 30 minutes for lunch. You still get your 1 hour. It's just that we're going to end up a little bit later. So thanks, everyone.